This presentation is on big data and automatic speech recognition and why the two are intimately connected. Actually, speech recognition might have been one of the first fields in which big data was the norm. So let's first go into the basics of speech recognition. Automatic speech recognition is based on computing this probability. This is the probability of a certain word sequence given a set of observations. The purpose is to find a word sequence that maximizes this probability. So what is the most likely word sequence given the observations? And this is something that is not so easy to compute, but we use Bayes' rule. And Bayes' rule ensures that we can rewrite this into this form, where this is the language model. And the language model gives the probability of a word sequence. This is the acoustic model, and that gives which observations are to be expected given that word sequence. And this one here is the probability of the observation in the first place, but this is independent of whatever word sequence you choose. So because this is independent, we don't need it to find the maximum. And that's the reason why we typically leave it out. So that leaves us with this equation. So the thing that we are now maximizing is this, which is the probability of observations given a certain word sequence, multiplied by the probability on the word sequence. So we are going to maximize this. So let's see how we're going to do that in general. What type of ingredients do we need? For the acoustic model, we typically use HMM models, hidden Markov models. And in this case, we have them on the phone level, so the individual sound level. They look like this. They have, in this case, 3 states, and you can remain in the state or you can go to the next state, but you can't go back typically. And what we have as a norm is that we have an entry state, a middle state, and an exit state of each sound in our lexicon of sounds. But we don't only have a lexicon of sounds, we also have a lexicon of words. So for example, we have the H sound and the E sound, and together they can form the word he. And we can combine the E, the I and the Z sound for is. Or we can create the word new by N, U and W, so that gives you new or new, which have this J sound or Y sound in between. And apparently 90% of the time we say new and 10% of the time we say new. So this is the lexicon of all the different words that we have in our system. But words have to be strung into a sentence, and for that we have this probability, so the language model, and this is the probability that he is pronounced multiplied by the probability that is pronounced and the probability that new is pronounced, and actually in this order. And then you get models for he is new, and this model then is asked, what is the probability that you can create the observations? So what we have is the production model, the acoustic model, and the word order model. So this is the probability that the words are produced in the first place, and this is the probability of the observations that this word sequence can provide. So why is this necessary? This is necessary because automatic speech recognition is actually an attempt to produce speech, in some sense at least. So what do I mean with that? Well, we have here a speech utterance, and that speech utterance that is processed with some type of standard signal processing, and that leads to so-called features. MEL, frequency septural coefficients, MFCCs typically. Well, you can make these into a picture, and so what happens with speech recognition is that we ask the speech recognition system basically to generate this picture. And the assumption is that if you put the proper words in order, and the proper sounds in order, then the correct sentence has the highest probability of actually producing this. So what are we doing within artificial intelligence? So we try to find the most likely sequence of sounds, and that most likely sequence of sounds is best able to create this picture. So we have the language model that is constantly creating all kinds of possible words. We have the pronunciation model that has been trained beforehand, and we have the acoustic models. And so if you ask all kinds of different words to be produced and word sequences to be produced, then one of them has the highest probability of actually creating this picture. And that is your recognition result. And this is actually quite a convoluted way of doing it, because we are checking, in principle at least, at any moment all the words possible. And all the possible words and all the possible sounds are constantly trying to explain this. In practice, we do this in a way that is fairly efficient, but we are always open for any possible sound, any possible sequence of words, and trying to make this. So this is an awful lot of work. And this awful lot of work needs a lot of parameters. And actually what we saw within automatic speech recognition is that we got an explosion of the number of parameters to be tuned. So let's go and search how many parameters actually are associated with this task. So this part here, the language model, well, suppose you have 1,000 words in your language model, in your statistical language model. It basically means that if you only look at the probability of a single word, in this case cat, then it's 1 of 1,000. But if you look at the probability of the cat, that is in principle 1,000 times 1,000, because the first word has a probability 1 in 1,000, and the other word has a probability of 1 in 1,000. Of course, this is not really the case. This is an approximation, but it's just to make the point and to get an idea of the order of magnitude. So if you have a language model that consists of 3 words, then now all of a sudden you have 1 billion possible options, and with 4 words the cat sits on, you have 1 trillion possible words. Of course, this sentence is in the real world more likely than all kinds of other sentences, so the actual probability should be a lot lower, but you have to estimate that, and that is all somewhere in your system. So also the unlikely ones have to be estimated, ideally at least. Then let's go to the acoustic model. Well, we have in English and in pretty much all other languages, we have about 40 different phones. So if you want to make a model of the sound A, then you have 40 different things. But unfortunately, language is very context dependent. So that means that an A of the A sound in a cat preceded by a C is actually different from a general A sound. And it's different from a ta sound and a pa sound and a ga sound, etc. So if you want to do this properly, we have 40 phones that can precede the A sound. In practice, this is less because some are not part of the language, but let's make this simple again. So then we have 40 times 40 for the biphone situation is 1600. But actually, not only the previous context is important, also the post content is important, and that leads to the triphone. And in the triphone case, you have 40 to the power of 3 is about 46,000 different triphones, and they all have to be trained because they are all different. And then even words, but maybe the TS combination is slightly different from a different combination. Then you have a quadriphone situation, and that leads to, in this case, 2.5 million different phones that you have to train. And in practice, you don't have to train so many because many will not occur, but this is just to get an idea of the order of magnitude. So we have big numbers here, and they are necessary in order to sufficiently approximate speech. So how does that then connect to the size of the database? So let's see. This is our word production model, but based on hidden Markov models. And those hidden Markov models, each of them, they represent an average and a sigma. So this is a standard deviation basically. And they don't do that in one dimension, but they do that actually in 40 dimensions. And each of these 40 dimensions, they correspond to a probability distribution that is typically not well described by a single average and a single signal standard deviation. So what we typically do is that we have so-called mixtures, and those mixtures approximate part of the probability distribution. So in this case we needed 4, so we need to estimate then 4 averages and 4 standard deviations. And we have to do that for 40 dimensions, and in order to say something sensible about each of these mixtures, we need about 100 observations to figure out what is the proper average and what standard deviation. And we have to do that not only for this state, but only for that and that. And we have to do that not only for this stage, but also for this state and this state. So we can multiply that with 3. And we have to do that for all the sounds in our lexicon. So all these sounds here, depending on how well we are modeling. And this leads to that we need about 50,000 different observations for each phone. And typically MFCCs provide us with 1,000 observations per second. So that means that we need about 50 seconds for each phone that we want to model. And that means then that if we want to make a phone level recognizer, which is probably not very good, we need about half an hour. For a biphone database, we need about 20 hours, which is still doable, but it's still not the best recognition system that we can make. A triphone system needs about 800 hours, and a quadriphone system needs about 32,000 hours. And this is, of course, really a lot of work. Well, this is already a lot of work. And for example, a modern database, LibreSpeech, has about 1,000 hours of audiobook. So with this rule of thumb, you can say that it is mainly triphone, and it has a number of quadriphone models as well. So it is clear that in order to approximate speech ever better, we need a bigger and bigger database. And in order to process a bigger and bigger database and to have more and more models and more complex language model, we need more and more computing power. And that connects us with Moore's law. So Moore's law is the observation, basically, by Gordon Moore, that the number of transistors and resistors on a chip doubles every 24 months. And basically that means that the computing power of computers doubles every 24 months. And so that means that the calculations that we can do per second and per $1,000 in doubles every 2 years. So, and that is a very, very clear and very stable development. So Moore made his prediction actually about here when he could look back, and then it has remained pretty stable until now. Maybe it's flattening off, and we need something new, optical, quantum, DNA computing or whatever. But this also drives artificial speech recognition. So let's see, same development time here starting in the 1960s, and this is the task complexity, so the speech recognition task complexity. Well, in the middle of the 1970s, someone called Jelinek at IBM noted that every time I fire a linguist, my performance goes up. And basically what he meant is that the best approach to speech recognition, according to him, was not a linguistic one, it was a statistical one. So it was not about firing linguists so much, but hiring statisticians and people like electrical engineers who know how to deal with complex formula and complex statistics. And that led to a new form of signal processing called MFCCs. Actually, there were multiple forms, but MFCC won out in the end. A little bit later, we found deltas, which is the temporal derivatives of those MFCCs, and the mixtures that you saw in the previous sheet. And then when I was working in automatic speech recognition, actually not much was happening. The only thing that was happening, basically, was that computers became stronger and stronger and stronger, and this whole paradigm became better and better and better. Not necessarily because we invented all kinds of new stuff, but because computers became more powerful. Okay, that needed all kinds of little algorithms, but there was not a real change. Some real change came in 2006 when deep learning was developed, but actually deep learning became only important here. So there are now deep learning speech recognition systems. And so what could these speech recognition systems do? Well, in the 60s, we were very happy if we could recognize isolated word, carefully isolated in a quiet environment, spoken by one particular person. And then in the 70s, we started working with connected digits like 4074, or connected words like this is a book. Or continuous speech, so that is when someone is describing, for example, what he sees in a microscope and without really producing very short constructed sentences. And here the database already became pretty big. Memory was not so expensive anymore. Here we went to continuous speech, which has a really big database. Most of those words were hardly ever spoken, so if you make an error, no one notices because they don't occur very often. So this is not necessarily a big jump. And here we went back to a smaller database associated with regular computer use, and Siri, for example, is here an example of. This all was associated with new developments on signal processing, and especially working with MFCCs. So in the beginning we had difficulty with clean speech, and then we could kind of deal with stationary noise, and then we were able to make adaptive noise models, and that is, I think, kind of the situation that we are still in here. So we have very good adaptive models that allow the whole system to work to some extent when the background noise is not too bad or too complicated. And it's a task of the user to actually ensure that the system can work in the first place. Speech recognition became ever better, and we measured that with all kinds of benchmarks. So this is a kind of a summary overview of all the different NIST, National Institute of Standards benchmarks until 2009. And we basically see that simple tasks like an air planning kiosk speech, which is very predictable speech, that became actually pretty good. Red speech became also, well, not really good, but this is a 10% error rate, but this is 20,000 words, so not that bad. Something that we were not very good at meeting speech. So microphone on the table and then figuring out what everyone is saying. That is still a really difficult task. And one of the modern things where deep learning plays a role is, for example, this one. And this is a really weird task. This is a task of making spoken books readable again. So this is actually pretty a kind of a non-task. So we have a book that is perfectly well readable, then we read it out, and we use a speech recognition system to make the perfectly readable book readable again. Anyway, this is a task that we have done and we are getting pretty good at. So, but it's not a very useful real world task. I hope that is clear. So, the systems are getting better. Also the systems here, this is rather old data, they are probably getting better and it's more usable. But there are still limitations, and the limitations are associated with the closing of the system that I'm always talking about. Yeah, so we can only make an artificial system work when we ensure it has controlled input and when it is protected from outside influences it cannot deal with and that prevent it from producing its predictable output. So what do we do to close the system? Well, we ensure that we have a lot of control over the input. So you have to speak close to the microphone. You have to speak words, accent, topics that can actually be recognized. Yeah, so if you use an English speech recognition system for Chinese, it will recognize whatever it can recognize as English, and it will be not perturbed at all by that. Another thing is that a training database basically closes the system. Yeah, so it defines what the system can and what the system cannot by simply including stuff in the database and excluding others. And database makers are very good in ensuring that the system produces something that is actually doable. And database makers are very good in ensuring that the system does a particular thing and is not confronted with particular other problems. And you make the system for a particular purpose and you exclude everything that does not help to create a system with that purpose. It also means that if there is no data of a particular type, then you will have no performance. So that also defines the system. And typically a training database is selected to be doable. And doable can still be really difficult for the field, but in general you see that the first year there's something like a 70% result, and then an 80% result, and an 82%, and an 84%, and an 85%, and etc. And then it levels off, and then people say, well, okay, we have learned enough from this, and we're going to a new training database, and we start with 70%. Again, and then we go up again. So there's always a certain development going on. And you see that this is leading to a whole field of people that basically say, give me the data and the labels and I build you a classifier. They don't necessarily know anything about the domain, but they know a lot about data and they know a lot about labels and they know definitely a lot about making classifiers. So then, what are the known problems of automatic speech recognition? Well, the list of these problems is basically stable since the 1970s, and that says something. So the problem is basically with normal speaking situations. The systems are not very robust to noise. They become more and more robust to noise, but we still haven't solved the problem of other speakers, of reverberation and room acoustics, of other environmental sounds at the background. So that this is a problem and remains a problem. Spontaneous speech is a problem. Kind of telling a story like this is kind of okay, but more lively speaking styles that are normal for everyone are more difficult, especially in a normal environment where you're sometimes close to the speaker and sometimes a little bit away from the speaker, and all kinds of other things are helping. Another thing is that speech recognition systems still produce all kinds of bizarre recognition results. So when they make an error, typically it leads to a bizarre recognition result. And in principle, there is no meaning attributed. It's basically what is the most likely thing that a system can produce, but it's not the most meaningful thing or the least bizarre result that can be produced. So that is an issue. If it's going wrong, it is going wrong really horribly. And another thing that should be a red flag is that the probability of a correct sentence is extremely low, in the order of 10 to the power of minus 500, well, even much worse. So basically the probability is zero. So the probability of a correct sentence is zero. But the probability of a sentence that is incorrect is even worse. And of course, it's even closer to zero. So we are working here in a domain that doesn't make necessarily a lot of sense. So if you have been listening to my last sentence, what is the probability that you recognized it? Well, it would be close to 1, and definitely not very close to 0 or 10 to the power minus 500. Then, of course, there always is a considerable processing load, which makes cloud processing with dedicated computers kind of a good idea, but that leads to privacy issues. For example, the Amazon systems that send stuff to a central computer, then process it, and then give you the results back. But the end result is that you have a system listening to whatever you say. So, in general, since the 1970s, we have a problem with dealing with the real, uncontrolled and open world, and that is the result of closing the system. So what can we then say? What is my conclusion, at least, is that the possibility space of automatic speech recognition includes pretty decent niche systems, but it might exclude human level performance. Yeah. So in order to work in the normal real world of humans, we might need a completely different system. And we might be missing the essence of the natural system. And if that is the case, and if the essence of the natural system is no longer in the hidden Markov model or the standard automatic speech recognition approach, then even bigger big data might not help. It will lead to ever better systems, but it will always ensure that the real problems, the fundamental problems, will not be solved. Because in order to solve the fundamental problems, we have to go back to the drawing base and somehow include the essence that the natural system has.